Hey folks, I hope y'all had a fantastic weekend. We're starting day 24 here. This is a section on equivalence relations. We talked about these at the beginning, at the end of class last time. Let's just go through the definition again. We have a relation on R, on A. Let's try this again. We have a set A, we have a relation R that's on A. What this is saying is that R is a subset of A cross A. So it contains ordered pairs where both elements of the ordered pairs are in A. It's an equivalence relation if all three of these conditions are true. If the diagonal is contained in the relation, every pair x comma x is in the relation for all x. And it's symmetric if anytime xy is in the relation, then yx is also in the relation. So either they're both in the relation or neither one is. But if you have one, you have to have the other. And it's transitive if anytime xy and yz are in the relation, then we can merge them and compose them and get xz in the relation as well. Okay? If this condition is true, we say that R is transitive. And we did a proof last time involving having the same remainder mod 5 being an equivalence relation. We're going to look at a similar problem here, but a little bit different. Let Z be the set of integers. Let R be this relation. Mn is in the relation if m plus n is an even number. And we want to prove that this is an equivalence relation. So we have to prove that R is transitive. Well, let's do them in order. We have to prove that R is reflexive. We have to prove that R is symmetric. And we have to prove that R is transitive. Reflexive uses one element. Symmetric uses two elements. And transitive uses three elements. So keeping that in mind, the first sentence for proving that R is reflexive is to let n be an integer. Okay? We just need to pick some arbitrary element out of the set of integers, and we need to show that n comma n is in a relation. Since n plus n is equal to 2n, and n is an integer, by definition, 2 times an integer is even, so n plus n is even. Therefore, n comma n is in the relation. So R is reflexive. All right, symmetric, we need two elements. So we'll call them m and n, b and z. All right. Now, we have two cases. If mn is in a relation, then so is nm. But if mn is not in relation, then neither is mn. So we consider two cases. There is a way to do this without doing cases, but assume mn is in R. Then m plus n is even. And so n plus m is even by the commutative property. And so n comma m is in R. And now we'll assume that m comma n is not in R, then m plus n is not even. And so n plus m is not even. Also by the commutative property, and therefore so n comma m is also not in R. So we've shown that anytime that mn is in R, then nm is in R. Anytime we've shown that mn is not in R, then nm is not in R. Transitive, we have to show three elements, so we'll call them k, m, and n. I could use L, M, and N, but my L's look like ones, so I'm using K instead. All right. We're going to assume that Km is in R and Mn is in R. What we have to show is that Kn is R. Then K plus M is even, and n plus m, m plus n, I'll do it in the correct order, m plus n is even. So there exist integers a and b such that k plus m equals 2a and m plus n is equal to 2b. Then k plus n is equal to k plus m plus m plus n minus 2m, which is equal to 2a plus 2b minus 2n is equal to 2 times a plus b minus n. And I'll continue this up in the top left corner by the closure property, by the closure axiom. A plus b minus m. That's an m, not an n. It looks like an m. Make that an m. A plus b minus m is an integer. And so k plus n is even. And so k comma n is in R. And that shows that R is transitive. Okay? And so that's the things that we have to show that we have an equivalence relation. All right. So we've seen a couple of examples of equivalence relations. What are some examples of things that are not equivalence relations? Couple of examples. X comma y is in R if x is less than y. That's not symmetric. If x is less than y, if x is less than y, then y is not less than x. So that would not be an equivalence relation. X comma y is in R if trying to think of an example of something that would be symmetric but not reflexive or transitive or something. So something that's symmetric but not transitive. If the absolute value of x minus y is less than 5. That's symmetric because if the absolute value of x minus y is less than 5, then the absolute value of y minus x is less than 5. But it's not transitive. Here's an example. If x and y were 2 and 6, so x is equal to 2, y is equal to 6, and z is equal to 9, then the absolute value of 2 minus 6 is less than 5, and the absolute value of 6 minus 9 is less than 5, and so y is in R and yz is in R, but the absolute value of 2 minus y is not less than 5. And so xz is not in R. So these are examples of things that would not be equivalence relations. So not all relations are equivalence relations, but we've seen a couple of examples that are. Now we've seen a couple of examples that are not. Okay? All right, let's move on. Equivalence classes. If we have a set and an equivalence relation on the set, we put square brackets around the element to indicate what we call the equivalence class. It's the set of everything that's in the set that is equivalent to x under that equivalence class. So let's go back and look at this example here, the example where m plus n is even. Let R be the equivalence relation in the previous example. So mn is in R if m plus n is even. And let's talk about what the equivalence class of 2 is. So it contains 2 because 2 plus 2 is even. It doesn't contain 3 because 2 plus 3 is not even. But it contains 4. It doesn't contain 5. It contains 6. It contains 8. Going backwards, it contains 0. 2 plus 0 is even. 2 plus negative 2 is even. 2 plus negative 4 is even. 2 plus 10 is even. The equivalence class of 2 is a set. This is a set. And it contains everything that satisfies 2 comma x is in the relation. Okay, everything that would complete the relation with 2. All right. So we have this theorem here. If A and B are 2 different equivalence classes, so these are these sets that we just looked at, then exactly one of the following is true. Either they are equal to each other, or their intersection is the empty set. Okay? So let A and B be equivalence classes. Of a relation R. Since they're equivalence classes, then there exist elements x and y such that A is the equivalence class of x and B is the equivalence class of y. Okay? Now we're saying exactly one of the following is true. Okay? So if this one is true, then 2 can't be false. Proving this, let me talk about the sort of this idea. If this is P and this is Q, then we have to show that if P is true, then Q is not true. And if we have to show that if P is not true, then Q is true. We have to show both of these. So first thing we'll do is we're going to assume that A is equal to B. Okay. Then, since X is in A, and A equals B, so X is in B, and so A intersect B contains X, so A intersect B is not the empty set. That takes care of this proof. Now we're going to assume A is not equal to B. And we're going to prove by contradiction here. We're going to assume suppose that A intersect B was not empty. Let Z be an element of A intersect B. Then X comma Z is in the relation because it's an A, and Y comma Z is in the relation because it's in B. Okay. But that's a problem, because that means that Z comma Y is in the relation because the relation is symmetric, and so X comma Y is in the relation. And if X comma Y is in relation, what that means is that the things that relate to X, where's my, right here, the things that relate to X, which are in A, are also the things that relate to Y, which are the things in B. Okay? And this creates a problem, because this tells me that A has to equal B. So this means that A equals B, since any element with, say, Q, with X comma Q in R implies Y comma Q in R, and vice versa. And so we have a contradiction. A doesn't equal B and A does equal B. And so by contradiction, we can't have the intersection being non-empty. A intersect B is the empty set. Okay? All right. So equivalence classes are either exactly the same or they are completely separate with no intersections at all, which it creates what we call a partition of S. That if I have a set S, I'll draw the Venn diagram, And I split it up into equivalence classes. The equivalence classes divide the set up into distinct pieces. They don't overlap. Either two elements are in the same equivalence class, in which case they're equal, or they're in different equivalence classes, in which case their intersection is empty. So let S be any set and P be a set whose elements are subsets of S. Okay? So this is a little tricky. These are our sets. The members of P are sets and not individual elements. But we say that P is a partition of S if their union is equal to S. I left off the equal to S at the end. And if I and J are different, then their intersection is 0. That's what we're getting here. So a partition of S, when we take the partition sets together, collectively they equal S, but individually their intersections are all empty. So they don't overlap each other. The equivalence classes for any equivalence relation always form a partition of S. Okay? This theorem we actually just proved a moment ago. So there are two things that we have to prove. We have to prove that two different equivalence classes have an empty intersection. We already proved that. The other thing we have to prove is that their union is equal to S. Okay? Let S be the set S1, S2, S3. Then, since S1 is in the equivalence class of S1, and S2 is in the equivalence class of S2, and so on and so forth, the union of the equivalence classes has to contain all of the elements in S. The union of classes must contain every element of S. And so the union of the equivalence classes will equal S. And statement 2, the different equivalence classes have an empty intersection. We proved that already. And so equivalence classes always form a partition of the set. So I want to back up for a moment, and we'll get to, we'll wrap up in a moment. We talked about this equivalence relation at the very beginning of class, that M plus N is even was the relation. We proved it was an equivalence relation. We saw that the equivalence class of 2 was the set of even numbers. The other equivalence class is a set of odd numbers. Every integer is either even or odd, and so these two equivalence classes include every integer collectively, but they don't, their intersections are empty. There is no element that's in both of the equivalence classes. This is a demonstration, this is an example of what this theorem is saying, is that once you have an equivalence relation, the equivalence classes themselves form distinct sets, don't overlap, but their collection turns out to be the original set. Okay? All right. Y'all take care. See you again on Wednesday. I've got office hours today at 10:30, and then we've got class in Surge at 2 and 4, 2:30 and 4 if y'all want to come by. Y'all take care.